Okay, I try to keep the microphone high. Um, so I think one of the reasons I was invited to give this talk is this graph, which shows the number of publications related to LSTMs in hydrology, specifically for rainfall runoff modeling over time. And also yesterday, there were two talks already mentioning LSTMs here in the morning. It is an architecture that in geoscience is applied more and more. And I want to talk about today why this architecture became popular and also why I think it's a good fit, but also why we think we should be careful and find ways to collaborate between machine learning and geosciences. Okay, the audience here is quite diverse. I will start actually giving some context of rainfall runoff modeling. When I got introduced, so my background is in civil engineering, and then I switched to environmental engineering. I learned about hydrology from essentially this diagram. I was always interested in modeling, even in civil engineering, and I was wondering, how do people actually model such a system? Like, how can you make a prediction about stream flow in a river down here when you have to account for all of these processes in the upstream area? And it was not until very late in my master that I learned about this one here, which is the ABC model, a very educational model, but it has a lot of similarities to our most complex physical models that we use in hydrology to predict stream flow. And the thing here is that we model systems as state space systems. So we conceptualize the world and the land surface into buckets. These buckets are updated over time from our weather inputs and in the end generate streamflow output. This is true for models like the ABC model. It's also true for more complex physical-based or conceptually based models like the HPV model. And it's also true for one of our most complex physical models like the MHM, a model with tens of thousands of lines of Fortran code. If you look at the code carefully, there's one equation that you will find constantly, which is this one. So I have, I think, 2 slides with equations. This is one of them. So the thing here that all these models have in common is that they abstract processes as storages. And these storages over time evolve as a function of the previous storage state, some model parameter that we calibrate, and then the inputs with some more model parameters, right? And the inputs could be outflows of other storages, it doesn't have to be precipitation, but this is like a general concept that you will find in any hydrology model. Yeah, and then if we look at how we set up these models, there's essentially 2 ways. One is single basin calibration. So we take one particular basin, one watershed. We have observations and we calibrate the model parameters, usually a handful, a few dozens, specific to the observations of one particular region, right? This usually gives us the best results for our model. Then there's regional basin modeling, where we have a second auxiliary model that we provide information about the catchment attributes. And then this auxiliary model, this meta model, generates parameters for this region. This is the only way how we can apply models globally, because in a lot of places we don't have observations. And then if we look at these 2 different approaches, what we commonly see is that the per basin calibration is significantly better than regional model calibration, right? So this is a cumulative density function over the Nash-Sutcliffe efficiency, a metric that they commonly use in hydrology. The further a line is to the right, the better. And we have 2 different models here, calibrated by different groups on the same data. And for both of these models, they were set up on the same regions, once calibrated per location. So these are the dashed lines, and once calibrated regionally. And if we look at the median model performance, right, this is drawing a horizontal line at 0.5 and then getting down the intersection. We see that for both of these models, as mentioned before, the per basin calibration is much better than the regional model calibration. Okay, now for the LSTM, we will make a small jump. I studied civil engineering and we don't have machine learning classes in university. So I had to teach me all this stuff by online resources. And actually, this is the class that I took and learned about LSTM. And this box is the entire equations of the LSTM. It's 6 lines of code, 6 equations, a super simple model. It's a recurrent neural network, which means it processes input time sequences time step by time step. The special thing about the LSTM is it has a cell state that it can learn to store information over time. And if we look at this equation, we see that the cell state of the model is a function of the previous cell state and something that they call a forget gate. And then there's an input gate and a cell update gate. Forget about the gates for the moment. If we rewrite this function, we see this equation. This is exactly the same equation that we have in conceptual storage models. Okay, so the forget gate here and the input gate and the cell update gate, you can see them essentially as walls and outlets that control how the information flows from the inputs to the storages, and then how within the system the information between the storages is reallocated. So this is really conceptually just a very general storage model. And in fact, I think there's so many similarities between the LSTM and hydrology model that in my very first paper, I spent an entire paragraph, it's longer than this, where I just tried to convince the hydrological audience that these are the same models, right? But the difference is that this model doesn't need hard-coded understanding of our processes in the model, but it learns the processes that are important to solve the problem and that are deducible from the data. And we will come to this again. What I actually spent my first 2 years of research with was trying to understand what the model learns. Because this is not a black box model. It's super simple to look at what the model learns internally in its cell states, right? So this is a graph of one model that I trained to predict discharge from meteorological input data. So just precipitation data, temperature, solar radiation, the same kind of data that we use in hydrology model. What we see here in the middle is SWE, snow water equivalent, from a commonly used snow model here in the US. And we see in orange one particular cell state of this model that has never seen snow data. It was never trained to predict snow. And then you see temperature and precipitation at the top of the bottom. And you can see that this model essentially learned snow all by itself, right? It's no surprise. Snow is like, in this particular catchment, it's a snow-dominated catchment. It's probably the most important process to get discharge right, but the model learned it and you can see it. You can understand it, right? Similarly, this is from like a very, very old presentation I gave during my master's. We found this other cell that if you look at it with precipitation data, I phrased it as, is this a water deficit cell? It's like an inverse soil moisture cell. Whenever there's precipitation, this cell drops, and then it slowly starts to raise again, and you could invert this and probably get soil moisture out of it, right? And we spent a lot of time initially when I started all of this research to just look at what did the model learn? Can we extract information from this model that we only train to predict discharge, but then get information about system states out of it? Because if we look at this again, there are a lot of processes that we actually don't know how to put into equations, right? And when we have this conceptual general storage model like the LSTM, maybe we can find a way how to extract knowledge from this model that we can then put into a conceptual model or a physics-based model to learn something about the process and then make our process-based models better, right? Because a lot of these processes at catchment scale are very hard to put into equation and connect with all of the other stuff that goes on in the system. The thing why I think most of the publications came along and most of this work was picked up was unfortunately not the interpretability stuff and not the discovery stuff, but this, which is the LSTM back then for the first time showed that there's much more information in the metrological data available than we are able to extract with our conceptual models. And also for the first time that you can actually get much better with a model that you train on all of these basins together instead of training per basin models, right? So here, this is again the same model. One's trained for each of these locations individually, one's trained on all basins together, and now suddenly the regional model is better. And if we compare this to a series of hydrological benchmarks that we had at the time, you see that here in blue, the LSTM became much, much better. And it was very easy to even improve upon this by just doing something like providing multiple metrological inputs to the model. Because it's a machine learning model, we are not forced to just provide a single metrological data product as inputs like we would do with physical models. Instead, we can provide multiple metrological forcing products at the same time, and the model can learn about synergies and differences in the weather products because there is no such a thing like the correct weather data at any location, right? And yeah, this is what in the end brought me to Google, where we use this kind of stuff to operate our global scale streamflow forecasting model that now covers more than 100 countries. And the thing here was that it was super easy to set up compared to existing models and gained a lot of performance for flood forecasting. But I'm here to more advocate for the science part of it, to not just treat this model as, oh, it's good at predicting streamflow, but much rather use it as a tool to learn something about the system, to try to explore what the model learns, and yeah, put more emphasis on collaboration between machine learning and, let's say, physical modelers or conceptual modelers, because I think this tool allows us to explore the information that is learned from the data, and eventually, maybe it can help us to get a better physical understanding of the system. It's also possible that we just learn that all that helps is just not relying on mass conservation or being better at uncertainty, accounting for uncertainty in the input data. But even if that would mean this is all that the performance gains come from, then this would also be an action item for us as conceptual and physical modelers to maybe rethink how we treat the uncertainty in the input data. And with that, I think I'm well ahead of time, but yeah, I'm at the end of my presentation.
Thank you, Fredrick. That was wonderful. We do have time for 2 questions or so. Okay.
That was very cool. I was a little confused by the simplification model that you showed, because it looks like just like a finite difference.
You mean the LSTM? No, it's super simple. It's really 6 lines of code that is just simple, very simple math. There's nothing behind it. It's really, really simple. So it's actually not a simplification at all. It's the so let's just look at it. This is really the entire model, right? And the only thing that happens here is you learn some weights, how your previous cell states are updated to the next time step, and some weights how your current inputs is distributed in the storages in the cell state of the system. And then you have non-linearity inside of it. And that's it. That's it. That's all it. Like, people always claim this is like a big black box, and people think about LSTM like these transformer models that we now use for large language models. It's a model from 1991. It's a super old model. It's a very simple model. It will take you one afternoon to write it yourself in Python code and to train this model. It's super simple. There's really nothing behind it. Yeah, so maybe not everybody in the room might be aware, but the way how we train these models is we take a single model, we take the meteorological time series data of one particular location, and we combine it with catchment attributes so that the model can learn between two different locations or hundreds of different locations, which locations are similar, which are different, what knowledge can I learn in location A that might be applicable to my location B. And these static attributes in most of these papers are really just kept static over time. And yes, they have a lot of intercorrelations in the attributes, which I don't think is like a huge problem at all. I just think that most of these attributes are not actually static. Land use changes over time. Wildfires burn forests. We increase cities or do all kind of stuff to our environment. And I think a very open research question is, and there are actually people from Colorado State's of a School of Mines working on this, so very close by. What happens if you train these models, for example, with information about forest of before wildfire and after wildfire? So you actually make these static attributes, catchment attributes, not static. Because some of these land cover changes have like a huge, measurable and visual impact on stream flow, right? So if we have this in our training data, can the model learn from it? This is current research. I don't think the intercorrelation of attributes is a huge problem, to be honest, but I'm happy to chat afterwards about this. Yeah, sure. Yeah, so the question was, what do we do or what happens if we have events in our forecast that were not part of the training data? So there have been a couple of research papers on this, on like predicting extreme events outside of the return periods of the training data. In general, the philosophy of this model or this modeling approach here is that if you train on global data, and we have like 40, 50 years of streamflow data across a lot of places in the world, like we train on tens of thousands of streamflow gauges, then eventually at some point you have seen a lot, not everything, but you have seen a lot of the events, maybe not in your particular location, but you have seen a big storm event in another location that might be similar to the location where you now see this event coming. So it's not completely unknown to the model. That doesn't mean that there's not a problem with the upper percentiles of extreme events that you have never seen. There were some studies specifically for flood forecasting that showed that the LSTM, even in this case, does a better job than existing conceptual flood forecasting models. So for flood forecasting, this was studied. I would not advocate that this is not a problem in general and not something to evaluate and maintain and like continue doing research on. It's not like perfectly solved, but for the operational flood forecasting, it's not so much a problem.